Hello, hello. Let me know when you can see and hear me. Hi, everyone. Hi, hi. Hi. Hello. Hi. Hi, Chinwendu. Yay. Hi. Hi, Arian. That message is from a while ago. Are you still there? Okay. If there is anyone watching over on TikTok, remember, I'm only answering questions that are on YouTube, so you can keep watching from there. But if you actually want to ask any questions, then make sure that you come over to YouTube, okay? And then you can get involved in the chat over there. So today we are focusing on some Group 2 and Group 7 chemistry. So what I've done, hi Mandy, yay! I have chosen a few past paper questions on Group 2 chemistry and Group 7 chemistry, and we're going to answer them, okay, with the explanations behind how we get there. So this will help us kind of cover a fair amount of the content in this way. Hi, Kimia. Yay. Oh, I'm so happy that you're here. Okay. So let's get started. We'll start with group 2, which is the simpler one, right? There's slightly less to focus on. Yes, JM, this is A level. So you'd come across this in year 12 of A level. Hi, Patrick. Yay. Hi, good evening. So for group 2, which statement is not correct? So strontium has a lower first ionization energy. Hi, Aria. Yay. A lower first ionization energy than calcium. So first, so this will be all a little bit of a heads up for you, Aria. Looking at group 2. Hi, Rija. Yay. Looking, I'm so excited. Let me try and chill out a little bit. Okay. Hi, Kira. Lovely, lovely. Hi, Abdurrahman. Amazing. So, if we look at our periodic table, calcium is above, let me leave a bit more space, is above strontium in the periodic table. I am well, Aria. How are you? I was thinking about our conversation at the end of our year 12 lesson with everyone, and I just really enjoyed it. I think we should do more stuff like that. Okay, so if we consider as we go down the group, we are going to have more shells, right? And therefore more shielding, which means it's going to take less energy for for strontium to lose its outer electron than for calcium. So strontium does have a lower first ionization energy. Okay, because if we think of calcium, how many shells does it have? Oh gosh, will I draw all of them? Calcium has 4 shells. Have I left enough space for strontium shells? No. Strontium has 5. So for strontium, there are more shells and therefore more shielding and therefore a weaker attraction between the nucleus and the outermost electrons. So less energy is required to lose strontium's outer electron. Okay, so it is our general trend, our NSDA. Okay, so not repulsion, it's about a weaker attraction. So strontium has more shells and therefore more shielding. Okay, Patrick, we've slightly changed the format for a couple of weeks where it's not quite asked me anything at all. It's asked me anything in relation to a topic of focus. So our focus topic for this week is group 2 and group 7. If you do have a quick question, I'm more than happy to answer it if it is relatively quick. Okay? Okay, no problem, Aria. I will see you on Tuesday. Okay? Indeed. So repulsion between electrons in outer shells and inner shells. I mean, I suppose, but we don't really think about it in terms of repulsion. We think of it in terms of shielding, because ultimately it's about the attraction between the outer electrons that we're trying to lose versus the positively charged nucleus. Okay, so the more shells there are, it's like there's more of a barrier between the nucleus and the outer electron. So there's going to be a weaker attraction between the nucleus and the outer electron. Okay, so strontium does have a lower first ionization energy than calcium because there'll be less energy needed to remove that electron. Okay, so it's not A. Strontium has a larger ionic radius than calcium. Again, we can see straight away. Hi, Pavith. Yay. We can see straight away that that is correct. So that's not our answer. We're looking for something that's not correct. Strontium reacts less vigorously with water than calcium. Well, if we think about our trend in reactivity as we go down group 2, it's going to, again, be able to be explained by our number of shells. Group 2 elements will want to react by losing their outer 2 electrons. Okay, so it's going to be easier to lose those outer 2 electrons if these electrons are further from the nucleus. So C is also true. So the correct answer must be D. Strontium hydroxide is more soluble in water than calcium hydroxide. And we know that because we know our trend in our hydroxides down group 2. So again, this is such a great question because it allows us to basically revise all of group 2 in just one question. Okay, so if we think about our hydroxides, so magnesium hydroxide, what's next? Calcium, strontium, barium. Okay, for the hydroxides, yes, indeed, Patrick, exactly that. Exactly that. As shielding increases, the first ionization energy is going to decrease because there'll be a weaker attraction between the nucleus and the outermost electron. Okay, so as we go down group 2, the solubility of our hydroxides increases. Absolutely, Chinwendu. And it's vice versa for our sulfates. So magnesium sulfate, calcium sulfate, strontium sulfate. Well, I don't think I've ever seen that written down before. That looks quite interesting. Barium sulfate. For our sulfates, the solubility decreases. Okay, Com. Hi, Com. This is indeed A level. So, Pavit, that's why you wouldn't have been told because these are just A level sessions at the moment. Once we start the GCSE ones, then you'll be notified in your newsletter. Okay. So, the way that we can remember this really easily is, oh, hang on. Oh, you're right. Oh, sorry, I can't read. It's C, obviously. We said it's C. Strontium is more reactive. How embarrassing. You're so right. Strontium is more reactive, so it reacts more vigorously. That's exactly what we said, and then I crossed out the answer. It's Friday. Okay, so you're absolutely right. Okay. Strontium hydroxide, thank you, Mandy. Strontium hydroxide is more soluble. So soluble is how easily it can dissolve in water, Patrick. Okay. And if we just remember one of these species, then we can remember the solubility trends for both. Because as Chinwendu said in the chat, which is great, barium sulfate we know is insoluble for a couple of reasons. We see it across our course. We see it because it's used as a meal before so that we can see X-rays. And it's used, barium 2 plus is our test for sulfate ions because it gives us a white precipitate. So if we know that barium sulfate, exactly, Mandy. So if we know that barium sulfate is insoluble, then we must know just by looking at our periodic table that the solubility for our sulfates decreases down the group. And then we know it's the opposite for hydroxides. So just remembering this, and you've remembered a whole bunch to be able to apply. Okay, let's go to our next question. Still on group 2. Which products are formed when magnesium reacts with steam? Hi, Snake. Oh my gosh, I'm scared. How are you? Don't bite me. Okay. Which products are formed when magnesium reacts with steam? What do we have? Lovely. So remember, magnesium is our exception, right? So typically, when we've got our group 2 hydroxides, they'll react just with cold water. But because magnesium is not very reactive, we'll react it with steam instead. Lovely. Hi, Marquinho. And instead of forming our magnesium hydroxide and hydrogen, instead, absolutely, we form magnesium oxide and hydrogen instead. Okay, so this is one of our exceptions. Our other group 2 metals, let's say we've got M, and we react that with just water, solid, liquid, then we would just produce our MOH2 and H2. Oh gosh, let's balance that. 1, 2, 3, 4. I think we just need a big 2 here. And then we're balanced. 4 hydrogens, 1, 2, 3, 4 hydrogens, 2 oxygens. Yep. However, for However, for magnesium as our exception, we'll say magnesium reacts with steam. So our state symbol instead will be gas, and we will produce magnesium oxide and hydrogen. And that quite nicely is balanced. Ooh, already. I'll put actually no, what will we put here? Let's put AQ. Okay. Here, magnesium oxide will be solid. Okay. Let's keep going. Again, any questions, please make sure that you're putting them in the chat as we go. And again, if there's anyone that is over on TikTok, if you want to comment, then, and you want me to see your comments, then come over to YouTube. The link is in my bio. Okay. Oh, we've had the answer for this already. Oh, quantum mechanics isn't covered, but the quantum mechanical model of the atom and orbitals is absolutely snake. Yes. Okay. We've had this answer already. Barium sulfate is used in medicine to produce an X-ray image. Okay, because it is insoluble. So it's not going to dissolve. Instead, the X-rays are going to be reflected so that we can see an image. Okay. Do we need to know that for OCR? I think so. Yes, I'm pretty sure. I think it's across the board. Okay. Okay, Marquinho, how are you finding it? D would be absolutely, Mandy. D would be for magnesium hydroxide. You're absolutely right. Okay. Let's look for a couple more key reactions. One that we see, not quite as often as the other ones, but it is on our specification, how magnesium is used as a reducing agent in the extraction of titanium. Let me give you a little bit more than that from titanium chloride. Let me not be mean. So, for magnesium hydroxide, the state symbol would be questionable. I'd say we can say solid, okay, but magnesium hydroxide, we say it's sparingly soluble, okay, so, but we can still say, let's say solid, depending on where we are, okay. Hi, M. Hi. Okay, so we have magnesium reacting with titanium chloride. Oh, wow, what do you do in general chemistry? That sounds very general. Lovely, Chinwendu. Why not MgOH, Patrick? Because magnesium is in group 2. Let's just do it quickly over here. So forms 2+ ions. Hydroxide is 1-. So when those come together, the charges need to cancel. So we need 2 hydroxides for every 1 magnesium. Okay. Snake, my favorite element is tungsten. What is yours? What will our products be here? So magnesium with titanium chloride, we would produce something plus titanium, right? Because we are extracting titanium. Lovely. MgCl2. Again, for the same reason that magnesium hydroxide is MgOH2, and then we just balance. Okay. Oh, tungsten is a great element. The symbol is actually W, which says a lot, okay, because it's incredible. Oh, wow. Yeah, Marquinho, that does sound really challenging. I remember, oh gosh, I remember those days. Okay, now The key here in this question, and whenever we're answering questions about redox, we need to pay really close attention. Hi, Batman fan. We need to pay really close attention to in what definition of oxidation or reduction they want us to use. So whether they want it in terms of oxygen, whether they want it in terms of electrons, whether they want it in terms of oxidation state. And we see here in this question, they want it in terms of oxidation state. So if we just went straight to, oh, it's lost electrons, we're not getting the mark. Okay, they've asked explicitly in terms of oxidation state. The oxidation state of the magnesium at the beginning was 0. Hi, Yashi. Oh my God, it's so lovely to have so many of you here today. And the magnesium in the magnesium chloride, it has an oxidation state of +2. Okay, so we can say that the oxidation state of magnesium increases or increased from, none on NMR spectroscopy yet. Those will come in due course. Okay, from 0 to +2. Okay, therefore, Mg was oxidized. Hi, Manal. Okay, so magnesium is the reducing agent because it was oxidized itself. Okay, or you could have said, therefore, it lost, Mg lost or donated those 2 electrons to titanium. Okay, but the key here is oxidation states. Who did I watch for my A levels? Well, back in my day, young OMS, I think that X is how, I think that's how I should say it. Let me know if it's not. Back in my day, we didn't really have YouTube videos to explain chemistry, right? We actually just had to use the textbook. And if it wasn't the textbook, then, go ask your teacher, basically. Rija, I've done a video previously, a public one, so here on my YouTube channel, covering some year 12 mechanisms. So if you go to my second Ask Me Anything, we focused on year 12 organic mechanisms pretty much the whole time. And also for us, anyone on my year 13 MES course, we are going to be doing a year 12 mechanisms lesson as lesson, I want to say 4 of our December module. Okay, so we're going to have a whole lesson on it later, but do watch that video as well to help you out. Okay, Omar. Okay, hi, Omar. Okay, I've missed a couple of hellos. Hi, Fahim. Glad to have you here. Hi, Pranav. Yay. Nucleophilic addition is wonderful. Such a nice one. Hi, Timo. Lovely. Last group 2 question before we go over to group 7. Explain why different observations are made when aqueous barium chloride is added separately to aqueous magnesium sulfate and to aqueous magnesium nitrate, and then write the simplest ionic equation for any reaction that occurs. Whew, that's a mouthful. So let's think about what happens. Let's do them as word equations first, just so that we can get our head around what's going on. Hi, Victor. So barium chloride, or should we go straight to symbols? The words are already feeling very long. No, it's okay. Barium chloride, let me not be lazy. Barium chloride plus magnesium sulfate. Lovely, Fahim. Thank you. Giving me some of those formulae in advance. Will produce, when our 2 salts react, they basically just they swap places, right? Because they are both soluble. Those ions will just be swimming around in solution, and then they'll just kind of stick together where appropriate. We will produce barium sulfate, and magnesium chloride. Okay. Oh, do I have tips for remembering the test for organic chemistry? Ooh. I think remember them in sections, right? So think of them as your halides and then your sulfate, and then what's the other one? Carbonate. Okay, and then just lots of practice, because the more practice that you do, they will become muscle memory. Flashcards, if that is a method that typically works for you, like a look and a cover, and testing yourself. Okay, yes, they do always swap, Elia. Oops, oh no. What's happening? Pen? Okay, come back. For our second equation, if we had barium chloride, not two, if we think about the charges, right? Plus magnesium, what was it? Nitrate. Our products are going to be barium nitrate and magnesium chloride. Okay, now to consider what our observations would be, we're going to put in the state symbols. Okay, yes, indeed, Yashi, sulfate is 2 minus. So they've already told us that barium chloride and magnesium sulfate are aqueous. Okay, so they are dissolved in water. Magnesium chloride is also aqueous. Barium sulfate, what would the state symbol be for that? What would the state symbol be? Considering what we've seen in our last couple of slides. Lovely. Great, great, great. Solid, because barium sulfate is insoluble. Okay. For our second one, again, aqueous, aqueous. So this specific reaction, Regia, isn't in the specification, but we should be able to recognize that barium sulfate is insoluble. And based on the context of the question, they're essentially telling us that nothing else is insoluble, right? They've said, what would be the different observations? If you're not expected to know anything about the other species, but you are expected this insoluble, the fact that barium sulfate is insoluble, that is something that you are expected to know. So once you know that, then the rest of it comes from that. Okay. So why would we have different observations? We would have different observations because barium sulfate, absolutely, application. Barium sulfate is insoluble, but barium nitrate is soluble. All nitrate salts are soluble. All nitrates are soluble. Oh, I've never taught AP chemistry. A-level chemistry, though, is challenging. Okay, anyone in the chat can attest to the fact it's a challenge, but hopefully a nice challenge, an enjoyable challenge. Okay, so our ionic equation for forming barium sulfate, we could write out all the ions and then cancel out anything that's aqueous, but because we already know that we are producing barium sulfate solid as our precipitate, we know what we must have started with, which is barium 2 plus and sulfate ions. And that's our ionic equation. Okay. If you wanted, again, to do all of the ions, cancel everything out, you're more than welcome to. But as soon as you're forming a precipitate, then your ionic equation is going to essentially be just the ions that are involved in that precipitate. Okay. This is year 12 chemistry. You may not have seen it yet in year 12 if you are in year 12. So this is either kind of some pre-learning for what's to come, or if you're in year 13, then it's great revision. Oh, okay. Omar, what would you recommend? Okay, I would recommend how you can still secure a good grade is build a timetable for yourself, okay, or ask AI to build a timetable for you that includes your topic, your year 12 topics, but also builds you enough time to make sure that you're able to consolidate your current topics as well. Okay, and then make sure that within that schedule, you've got breaks scheduled in there, okay, and that your revision strategies are active revision strategies. So not just, I'm going to read the textbook, because as soon as that textbook is closed, nothing has happened, okay? So you're answering exam questions, you're testing yourself with flashcards and multiple choice. Okay, so make it as active and applicable as possible. Okay, this is pretty much every exam board. This you would see in AQA, you'd also see it in Edexcel, and I'm pretty sure you see it in OCR as well. Okay. Around, yeah, 40, sometimes less, depends on the paper. But lots of the year 12 content is kind of I keep like doing this. Is kind of woven into the year 13 content. Okay, so you kind of see them both start to work together. Okay, let's keep going. Yeah, let's do 15 more. It's meant to be half an hour, but I always add an extra 10 minutes because I like to finish what we started, right? How come you don't need to balance with water and H+? This isn't a half equation. This is an ionic equation. Okay, so that would be half equations. That's like the redox, loss and gain of electrons. Okay, this is already balanced. Okay. Explain the trend in boiling temperatures of the elements on descending group 7. Okay, anyone in GCSE, you can answer this as well. Again, we're not talking about reactivity, we're talking about boiling temperature. When we're thinking about boiling temperature, we are considering the structure and what holds that structure together. Aliyah, it depends on the year. Some schools start Key Stage 4 in year 9, others start it in year 10, so it really depends. I can't answer that question. Only you know the answer to that question, whether biochemistry, maths, or physics, biomaths, because whichever one is easier for you is going to be the easier one. Okay? Because, for example, for me, chemistry, so much easier for me than physics. Other people, physics is so much easier for them than chemistry. So it really, unfortunately, I can't be that helpful there. That has to come from your heart and your grades. Okay? You are absolutely, yes, year 12 is A level. Yes. So you're absolutely right. The boiling point will increase. Why? Again, let's consider what type of structure they have. Lovely, Chinwendu. So they have simple molecular structures. So they exist as simple molecules. And so they are held together by intermolecular forces, specifically van der Waals forces, or depending on your mark scheme, London forces. As we go down the group, again, we're not talking about shells and shielding. That would be about reactivity. We are talking here about structure. And structure here, because we're talking about simple molecules, is about what's holding that structure together. Because we've got simple molecules, these just diatomic molecules, they are held together by weak intermolecular forces. Okay, they don't have dipoles because it's just the same element. There's no difference in electronegativity. Okay, so as we go down the group, what happens to the molecules that would make the London forces or any intermolecular force stronger? What happens to the molecules as we go down the group that makes these van der Waals stronger? Why are the van der Waals? That's point 1. They get strict, but why do they get stronger? What becomes larger? Why are there more forces? More electrons. BK, shout out to you. Excellent. Again, it's not necessarily about atomic radius. We're talking about the size of the molecule. So we're saying that the size of the molecule increases, or you could say the number of electrons increases, because that's going to increase the size of the electron cloud. Okay, again, we're not breaking any shells. No, you're not answering the right thing, unfortunately. It's really important when we're answering these questions that we can distinguish between when we're talking about reactivity and when we're talking about structure and bonding. Okay, when we're talking about reactivity, that's how easy it is to lose or gain electrons. Okay, whereas here, when we're talking about structure for boiling temperatures, that's about the structure and what holds that structure together. Okay, because these are simple molecules, they're held together by intermolecular forces. Yes, our fourth point is that, therefore, more energy required to overcome or to break the intermolecular forces. Again, if you want to be specific and call them Van der Waals or London forces, absolutely fine. Okay. Alexis, you wouldn't get marks here for talking about the states because it's not explaining why the boiling points are getting higher. Incognito, the number one, yay woo woo, the number one A level that I think goes the best with chemistry, I think they are best friends, is maths. Okay. If you've got maths with chemistry, wonderful. Okay. Again, biology, it's nice, but it doesn't necessarily, actually, no, and to be fair, biology does help your chemistry, but only really for one topic when you're doing like the biochemical, the biological molecules. Okay. But because there's maths all the way throughout your chemistry course, maths is chemistry's best friend. Okay. Okay. Oh, Alexis, lovely. Are we happy with, let's just stay here for a moment, making sure that when we are talking about boiling or melting, we are talking about the structure. We're not talking about losing or gaining electrons and shielding and all of that stuff. Okay, we're talking about, oh no. Oh, okay, sorry, I lagged for a second. We're talking about the forces or the bonds that hold that structure together. Okay. Yeah, biology and chemistry for medicine, the kind of most kind of elite combination for medicine, if you look at some of these top universities, biology, chemistry, and maths, right? If you look at universities like Cambridge, for example, most of their medical students did biology, chemistry, and maths. That doesn't mean that's the only combination, but it's a very competitive combination. And if your school allows you to take a fourth A level, that's even more competitive. But if it doesn't, then you're not going to be penalized for that. Okay. Let's stay together for 10 more minutes and look at a couple of the reactions within our group 7 chemistry. Hi, Devansh. Yay. BK, sorry, I think I missed your earlier question. What do you mean by outside of A levels? Chemistry and geography? I mean, why not? I would say maths is the best friend of chemistry for A level, but that doesn't mean that you can't take any others. Oh, I see. BK, it depends on the exam board. So AQA typically still uses Van der Waals. OCR and Edexcel will only accept London forces. Okay, AQA, if you said London forces as well, they have to accept it because it's correct. Okay, what is atomic radius? That's the size of the atom, and so then that will determine essentially how easy it is or how hard it is to lose or gain an electron. To be fair, to a certain extent, maths is it's not, I mean, it's a core subject for a reason for a long time. A level is much harder than GCSEs, yes. Okay, let's say a grade 9 at GCSE would be a grade E at A level, maybe a U. Okay, there's a massive jump. Okay, yeah. You have to work really hard. Yeah, it's a challenge. Even for students that do incredibly well at GCSE will still find A-level chemistry a challenge, okay? It's not a joke. And I don't say that to scare you off. I say that so that you know what you're getting into and you choose it knowing what you're getting into and you're prepared to work hard for it. Because if you're not prepared, if you want to do A-level chemistry and you don't want to work, then you better be the most genius that ever existed that doesn't need to put in any work. Okay. But if that's not you, you need to be prepared to work. Okay. I hope you do choose chemistry and I hope you're in my classes in year 12 and year 13, Yashi. Okay. Let's do some reactions of our halides, our solid sodium halides. So solid sodium chloride reacts with concentrated sulfuric acid. We get misty fumes. So we have got H2SO4 plus NaCl. Okay. And here, oh, close for heme, very, very close. Because chloride rather, so Cl minus, oh, let's just put it here. Cl minus is a weak reducing agent. Okay, because the reducing capability increases as we go down the group. Iodide, that's the strongest of them all. Well, I mean, let's pretend astatine doesn't exist for now. So when we react sodium chloride, it will reduce the sulfur A in our sulfuric acid. When we react sodium chloride with sulfuric acid, because chloride ions, are the weakest reducing agent, they are not able to reduce the sulfur at all. So instead, the products that we get are just a salt, so sodium hydrogen sulfate, and HCl. And this is not a redox reaction. This is just an acid-base reaction. Okay, because the H2SO4 has donated an H plus to the Cl minus. So the H2SO4 is acting as an acid and the NaCl is acting as a base. There's no H2S. That would require reduction of the sulfur. Chloride is not able to reduce the sulfur in sulfuric acid. It's too weak of a reducing agent. Okay, so the misty fumes that we see are from the HCl. Okay, hi Ian. Okay, wow, Alexis. All the best of luck and make sure you keep coming to these lives to help you out or even have a look at our courses as well. Daro, that is a good question that I don't have the answer to, unfortunately. Okay, but I think if the demand gets high enough, then we will ultimately. But at the moment, because the vast majority do either OCR or AQA, those are the two courses that we offer at the moment. Okay. An A star for heme is around 85-ish%. Okay. Oh, if you're starting year 12 next year, you can absolutely join our year 12 course because our year 12 course, I've got students from every exam board, right? Because it's mostly the same. Now, when it gets to year 13, that's when it splits. So I would say still come over for year 12. Why is Cl minus the weakest reducing agent? That's a great question. Well, let's consider Cl minus, in order to be oxidized back to Cl2, what does it need to do? What does it need to do? To go from Cl minus to Cl2 in terms of electrons, what will it do? If it gains electrons, it will become 2 minus. So it's not going to gain electrons. It's going to lose electrons, lose 2 electrons. Oh gosh. Yeah. Okay. Now we can think of this the other way round as we thought of those metals. Okay. If we have a chloride ion with how many shells? 3 shells versus an iodide ion with 5 shells. Whoa. Whoa. Okay, which one is going to lose an electron more easily? Which one will lose an electron more easily? Absolutely. The iodide. Yeah. Because more shielding, so more shells, more shielding, weaker attraction. Between the nucleus and the outer electron. Okay, so I'll just show the outer electrons, right? So if we look, oh no, come back. If we look at our chloride ion, it's going to be a lot harder to lose that electron than it will for iodide, where that outer shell is further from the nucleus. Okay, so iodide is the stronger reducing agent. Okay. Ooh, incognito. I am going to take note of that. So not this live, but in a future live, I will absolutely do that EDTA question. Okay. BK, yeah, this is essentially is very similar to how our MES lessons are. In our MES lessons, they're often, actually no, to be fair, this is quite structured. They're often even more structured because it's like content and then practice as opposed to going straight to exam questions. Okay. But yeah, this is a nice taster if you're interested in MES. Okay. Let's do our last question. I know I said 10 more minutes, but if you need to go, bye. I won't hold you. Okay. But please do stick with me. Ooh, Omar, that is a great idea, possibly in the future. Okay. We are constantly, trying to grow and, figure out what's next. So I think that's a great idea for in the future. Okay. So, solid sodium iodide also reacts with concentrated sulfuric acid. Steamy fumes are produced initially, but a second reaction then takes place. Give an observation that you would expect for the second reaction and write appropriate equations to show the reactions taking place. Okay, so with all of our sodium halides and concentrated sulfuric acid, the first equation is exactly the same, okay? The first equation for all of them is, to be fair, BK, for MES, our lessons are a set time because there's like a timetable that, there's lots of other teachers that have all got their classes as well. Because this is more kind of like loose, right? I can just kind of stay on because I'm not interrupting anybody else's lesson, if that makes sense. Okay, but the MES lessons are an hour apart from year 13, which is an hour and a half. Okay, so just like our last one, we have our sulfuric acid, we have our sodium iodide, and exactly as before, our first equation, our products will be, tell me in the chat, what will our first products be? Oh, lovely. HI, wonderful. HI and NaHSO4. Okay, so just, or you could be BK, it could also be sodium sulfate, but then it would have to be Na2SO4, and then the balancing gets a little bit more involved. Okay, so if you write the equation like this, then you don't actually need to do any fancy balancing. You can just leave it exactly as it is. Okay, and so just as before, we have an acid-base reaction where the sulfuric acid is acting as the acid, the sodium iodide is acting as the base. But because iodide is a very strong reducing agent, right? I minus is a strong reducing agent, the reaction doesn't stop here, right? For chloride, it stopped there. For iodide, it does not. The HI goes on to react with more sulfuric acid, and it's now able to reduce the sulfur in the sulfuric acid. Okay, not to gain an electron, to lose an electron. Okay, it's a reducing agent, which means it causes something else to be reduced, and itself, it's oxidized. Okay, that's a key term that you will learn more about in A level. Okay, so if it's a reducing agent, it reduces something else. Okay, now our products, there are two products that are going to be the same regardless. You are going to produce the halogen, so iodine. You're going to produce water, and then you're going to produce a sulfur-containing compound, okay? Because iodide is such a strong reducing agent, it is able to reduce the sulfur down to +4 oxidation state in SO2, the 0 oxidation state in S. Am I behind myself? Not quite. And the -2 oxidation state in H2S. Yes. Now you can choose any of these three because any of these three compounds can be formed. I think the more interesting one to write is the H2S, right? So we'll do that. We can just choose one of them. And then we balance. H2S, yes, smells like rotten eggs. I've got a reel on it coming out soon about why we don't like sulfur compounds. Okay. Balancing this, the way that this can be balanced really easily, in my opinion anyway, is by looking at the oxidation states. The oxidation state of the sulfur is +6, right? Because we've got -8 from the oxygen and then +2 from the hydrogen. So Farouk, yes, this is A level only, but feel free to stay if you like. And then the S in the H2S is -2. So if it's gone from +6 to -2, how many electrons has it gained? How many electrons has it gained? Quick maths. More than that? More than that? Timo, yes, absolutely, 8. Okay, 8 electrons have been gained, which means that we must have needed 8 iodides. So then to balance this, it becomes really easy. 8 HIs, right, to make sure that we've got enough electrons being lost. Then we can balance our I2 with 4 of those. And then we balance our waters. How many waters would we have? 4? Because of our 4 oxygens. Please tell me that's balanced, otherwise that'll be really upsetting. Let's check. We have got 8 + 2, so 10, 10 hydrogens on the left, 8 + 2, 10 hydrogens on the right, thank goodness. We've got 8 iodines on the left and the right. We've got 1 sulfur, and we've got 4 oxygens. Excellent, balanced, yay. Woo woo. Or AA if you're in year 11. Okay, so this equation, we can balance this and write it in the same way, whether we've got iodide, Hi, or whether we had bromide, HBr. The only difference is instead of I2, we would make, let's do just a quick aside before we go. If it was HBr instead, then we would make Br2 instead. We would still make H2O, and we wouldn't be able to go all the way down to H2S. Instead, we would just be able to make SO2 as our sulfur compound. Close BK, it wouldn't be I2 and H2, it would be 2HI. And then 2 NaI over here, yeah. Okay. The chemical that smells, yeah, it smells really bad. It smells disgusting. It smells like rotten eggs. H2S smells like rotten eggs. Yeah. Okay. We have stayed here for ages, but time flies. I mean, I was having so much fun. So, oh wait, we didn't say our observation. Oh, we did. Rotten egg smell. That is our observation for our next one. Okay. Yes, yes, at volcanoes. BK, yes, if you did it the sodium sulfate way, so this way, absolutely still valid. Just make sure that you balance it correctly and then absolutely fine. Yeah. Okay. Yay. Really well done. I'm so glad that so many of you were able to join me this evening, this Friday evening. You spent doing chemistry with me. I mean, if that's not commitment, I don't know what is. Okay, I hope to see lots of you again in future lives. Again, make sure that you see on my TikTok and my Instagram, whichever one or both. I'll always post a story or a video that says what time it's going to be that particular week. Okay, so pay attention to those so that you don't miss any. Yay. All right. Have a lovely rest of your evening. Have a lovely weekend. And I will see lots of you next week in our next lesson. And some of you, I will see you in our next live, hopefully. Okay. Yay. Okay. Bye, bye, bye. Yes, Wednesday, Chinwendu, indeed. Okay. Bye, everyone. Bye, bye, bye.